Hello, Anand Tiwari sir. Please stop sharing. Shanidul sir, we can start now.
Okay. So
Anand sir, please stop sharing. Your screen is sharing.
Yes, Asher sir, can I proceed?
Yes, you can proceed.
So a very good afternoon to respected resource person and speaker, Dr. Sudip Biswas sir, senior faculty members, my colleagues, and all the participants. So I welcome you all to the second session of day 3 of 1 week short-term course on future opportunities and challenges in 5G technology, which is organized by Department of Electronics and Communication Engineering in association with IIIT student chapter of Madanapalli Institute of Technology and Science, Madanapalli. So now I am handovering to Ashish sir to introduce our today's speaker about Dr. Sudip Biswas sir. Yes, Ashish sir.
Okay, thank you, sir. So now I'm a very good afternoon, one and all. Now I am going to introduce today's speaker, respected Dr. Sudip Biswas sir. Dr. Sudip Biswas sir is an assistant professor in the Department of Electronics and Communication Engineering at the Indian Institute of Information Technology. He joined IIIT Guwahati in August 2019. Prior to that, he received his PhD degree in digital communication in 2017 from the University of Edinburgh, UK. Following that, he worked at the Institute of Digital Communication in University of Edinburgh as a research scientist from 2017 to 2019 on optimization and signal processing for 5G and WAN communication. He also have industrial experience with Tata Consultancy Service in India, Lucknow and Kolkata, where he held the position of Assistant System Engineer from 2010 to 2012. He was a member of Conference Organizing Committee for IEEE International Workshop on Signal Processing Advanced in Wireless Communication held at Edinburgh in 2016. He is currently in the Technical Program Committee for IEEE Globacom 2020 selected area in communication, machine learning for communication, and have previously served as a CR in the session performance analysis in SPAWC 2020. Furthermore, he have been previously involved in 2 EU FP7 project, remote radio heads and parasitic antenna arrays, and dynamic license share access. One DST UK IERI project on wireless S caching, and one EPSRC project on non-orthogonal multiplexes. Currently, he is leading SERB funded project titled Signal Processing for Coexistence between Radar and Future Communication System SPI. He is also a coordinator of Memorandum of Understanding signed between IIIT Guwahati and National Sang Yat-sen University, Taiwan. He has already published many papers. More than 30 papers are published in IEEE transactions and LGVRs and Spinzer journals. Now I welcome Dr. Sudip Biswas sir in this short-term course and request sir to address the valuable talk in-band full duplex for next generation wireless communications. So welcome, sir. Sir, you are not audible.
Yeah. Sorry, my mic was on mute. Yeah. So
Yeah.
thank you, Tasher, for the introduction. Am I audible now?
Yes, you are audible now, sir.
Okay. Okay. So good afternoon, everyone, and happy Vijay Dashami to everyone. Today is Vijay Dashami, so we are all celebrating the win of good over evil. So happy Vijay Dashami, everyone. And so let's begin our talk. So I'll first share my presentation, if that's okay. Can I share my presentation?
Yeah, yes, sir, you can share.
Just give me a moment. So I've shared my entire screen. So is my screen visible?
Yes, sir. Visible, sir.
Okay. So in the meantime, during the presentation, I'll just switch off the video when you're done sharing. Yeah. Okay, the video is closed anyway, so that's fine. That's not an issue. So I'll just start off with the presentation. Yeah. Okay, so the title of my talk today will be Full-Duplex Communications for Beyond 5G Networks. And during the course of the talk, I'll cover topics related to 5G in general. Then I'll also look a bit into what are the standards of 5G and what has been considered to be the parameters or what are the typical 5G parameters that have been proposed. And then I'll talk about a technology known as full duplex communication that is not in 5G actually, that is something for beyond 5G networks. So that is going to shape how we speak about future wireless communications. So that is a technology that I'm going to focus on today. And by the end of the presentation, I'll also shed some light onto some future research directions that the world is headed with respect to 5G or, for that matter, full duplex communication. So this is the basic outline of the talk. So by the time we finish this talk, so I hope that you will be able to answer the following questions, like what is 5G and how is 5G different to what currently today we are experiencing LTE. Then where's the 5G being used? How fast is 5G? Is 5G available now? Also, do I need a 5G phone to experience 5G? Those kind of questions and many more you'll be able to answer. You'll be able to answer by the end of this talk. Okay. So this is I'll start with a basic outlook of the mobile data traffic. So this picture that you can see on the screen is a projection of the mobile data traffic per smartphone in gigabytes per month. The source is Ericsson. And as you all know, since the past couple of years, we have been restricted to our homes due to COVID-19. And the new norm is remote working. Even today, as I am giving this presentation, many of us are at the comfort of our home, and I am giving the presentation from my home. I am giving the presentation through my uh, mobile internet, and many of you may be also looking at this presentation from your mobile internet. So this remote working due to COVID-19 has been one of the traffic drivers during 2020 and 2021. Okay. And for example, in India, this traffic growth is seeing an upward trajectory and remains in the region of the with the highest monthly users per smartphone. Okay, so it's around 15.7 gigabytes. So this, as we just saw, so people are more reliant on their mobile networks nowadays to stay connected as well as work from home. And this has contributed to the average traffic being increased from 13.5 gigabytes per month in 2019 to 15.7 gigabytes per month in 2020. And of course, COVID-19 has definitely uh, affected that. And in many parts, because India is, though we all are privileged to have high speed internet connection, many parts before 2020 in the villages we're still using 2G and 3G, but COVID-19 has made even 4G accessible to those parts of the country. And if we look at the projection, so the total traffic is projected to quadruple of what today it is. So reaching around 35 exabytes per month in 2026. Okay. And the reason, basically, the number of smartphones are increasing, and rural areas which previously used to be deprived, now they are also seeing this advent in the increase in smartphone and the increase in LTE connectivity. And each smartphone now uses more data. As you must also, as many of you must be doing at your own homes, we are moving away from digital TV. We are moving away from DTH services. Now we are more interested in OTT platforms, right? Netflix, Amazon Prime Video, all those OTT platforms. We watch most of our TV shows on OTT platforms. So the demand for data is increasing every day. So in India, if you look by the numbers, by around 2026, an additional 390 million smartphone subscriptions are expected, and taking the total number of smartphones close to 1.2 billion. So by the year 2026. So this is a chart of global mobile data traffic. Again, the source is Ericsson, which is the y-axis shows the traffic in exabytes per month. And you can see that it is expected to grow by a factor of 4.5 to around 226 exabytes by 2026. Okay. Now, how can a mobile communication network achieve these demands? The networks such as Airtel, Vodafone, BSNL, how can such mobile communication network achieve such exuberant demands? Okay. Now the answer to that is 5G. So by 2026, it is expected that 54% of the total mobile data traffic will be carried by 5G networks. Now, the natural question that comes to mind is, what is 5G? Since this workshop is on 5G, so you must have already heard talks. Some of you may have already heard some talks that is on 5G, and you may already know by now what 5G is. But for the sake of completion, I'll have to go through the basics of 5G again. So I'll try to keep it as short as possible. Because the term 5G is still, though it has been clearly defined, but it still is something of a different person, a different industry, different company, they have their slightly different definitions. So with respect to 5G, what means the most common thing is that 5G is nothing but the fifth generation mobile network, right? And it is another new wireless standard after 1G, 2G, 3G, and 4G. So 5G is the next big thing that is quite understandable. Now this 5G, it enables a new kind of network that is quite different to what 1G, 2G, 3G, and 4G were. So basically, it is designed to connect virtually everyone and everything together, including machines, objects, and devices. So 5G basically is meant to deliver higher multi-gigabytes peak data speeds, then ultra low latency, more reliability, massive network capacity, increased availability, and a more uniform user experience to more users. So basically, this high performance and improved efficiency, they empower new user experience, and as a result, can connect new industries. So this is 5G in a nutshell. Okay.
Now, two major trends are behind the race to this 5G. What are they? One is explosive growth in demand for wireless broadband that can carry video and other content-rich services like 4K video, 8K video, those kind of things. And another one is Internet of Things, machine-to-machine communication, all those things, where large number of smart devices communicate over the internet. Okay, so before we go into what 5G is in more details, so one might ask the question that how is 5G different, right? So 1G you already know if you have studied mobile communication or wireless communications. 1G was the first generation of communication and delivered analog voice communication. Then 2G introduced digital voice. Okay, so for example, CDMA was introduced. Then 3G brought mobile data. 3G brought mobile data. For example, CDMA 2000 was one of the standards. Then 4G brought the era of mobile broadband. So there is a difference between mobile data and mobile broadband. Mobile data was just that you can you can browse your mails, you can open a website or something like that. But mobile broadband is speed. You could have, so the later part of LTE even reached up to gigabit speeds, gigabit LTE, which are known as gigabit LTE. So 4G LTE, it ushered the era of mobile broadband. So this 1G, 2G, 3G, and 4G all have culminated to 5G. So 5G basically is designed to provide more connectivity than was ever possible before. Okay, it is a unified, more capable air interface. It has been designed with an extended capacity to enable next generation user experience, empower new deployment models, and deliver new services. As I was mentioning a couple of slides before, so with high speeds, superior reliability, and very little latency, 5G will basically expand the mobile ecosystem into new realms of possibility. Okay, 5G will impact every industry. It will impact the transportation industry. It will impact the healthcare industry, like remote healthcare. Then it will impact the agriculture industry. It will impact the logistics industry, and many more. Okay, so this is how different 5G is to previous networks. Now 5G is actually being deployed in waves. So it is so big that it is not possible to make an overall infrastructure change to deploy such things. So if you want to deploy everything at the same time, it will require so much change that the world will break down. So you cannot deploy everything at a time. So 5G is being deployed in certain waves. So the wave 1 is basically fixed wireless access. Wave 2, consumer cellular. Wave 3 is Internet of Things. And wave 4 are some future use cases like mission critical applications for ultra reliable low latency communication. Now in the US, the wave 1 was started from 2018 itself in the US. Then after that, the consumer cellular started around 2019, and IoT for 5G has also started around 2020. Unfortunately, in India, we are lagging a bit with respect to that. We are going to come to that, why the reasons that we are lagging behind in terms of deployment of 5G. But for now, just understand that wave 1, wave 2, wave 3, and wave 4, this is how 5G will be deployed around the world. So in India also, for example, let's say if in 2020, later half of 2021 or 2022, we are going to see 5G, then we are going to first see the fixed wireless access. and soon to be followed by consumer cellular. Anyway, this is a common diagram that I like to show everyone when explaining what are the verticals that 5G is going to cover. So this triangle basically encompasses all the verticals that 5G is supposed to cover. Okay. So on the top, you can see EMBB, or Enhanced Mobile Broadband. And on the bottom two vertices, you can see the massive machine type communication, MMTC, and ultra reliable low latency communication, URLCC. So EMBB basically encompasses the very high data rate applications like streaming 4K and all, then cellular, then cloud gaming, those kind of things. And MMTC basically encompasses smart homes, then industry 4.0, etc. And URLCC basically encompasses the mission critical applications like autonomous driving and tactile internet and all those things. So basically, for example, let's say UAV. If let's take the example of UAV, it's centered around in the middle. So basically, while it also requires some enhanced mobile broadband capabilities, it also requires ultra reliable low latency communication, because a drone, an unmanned aerial vehicle, it might be streaming directly some videos to a ground station, so it will require enhanced speeds, but at the same time it also needs very low latency, right? So these are basically the verticals of 5G, which encompasses these three topics. So these are some of the requirements that 5G will satisfy, like latency in the air should be less than 1 millisecond, then latency end-to-end should be less than 10 millisecond, and connection density should be around 1 million nodes per kilometer square. Area capacity should be around 10 terabits per second per kilometer square. System spectral efficiency should be around 10 bits per second per hertz per cell. Then peak throughput for the downlink should be around 10 gigabits per second. Energy efficiency should be 90% more than what LTE offers currently. Reliability should be around only 1 out of 100 million packets lost. So these are some very big claims that 5G is going to give us. Now, these stuffs are who decides these stuffs? There are certain cellular standards, there are certain cellular bodies that are responsible for standardizing this kind of parameters or technologies and everything. So you must have heard about the ITU, the International Telecommunication Union, which is a United Nations agency. It is tasked with coordinating the telecommunication operations and services worldwide. Now, this ITU provides guidelines by outlining the requirements for cellular operation. So there is a body known as 3GPP, known as Third Generation Partnership Project. It follows these ITU guidelines to develop mobile specifications. Okay, and then the ITU evaluates the specifications. If it deems fit, it will give approval, and it will issue the compliance certificates. Now, India also has a standardization agency known as Telecommunication Standard Development Society, TSDSI. So it is an autonomous organization that develops standards for telecom and information and communication technology, ICT products and services in India. So apart from 3GPP, 3GPP is a worldwide body. Everyone follows 3GPP, but India also has something, TSDSI, which has its own set of standards. And but again, whatever standards TSDSI develops, it has to be passed through, it has to be approved by ITU again. And as I was mentioning why 5G in India is slightly delayed. One of the reasons is worldwide 5G is standardized through 3GPP. In India, 5G is being standardized through TSDSI. So TSDSI has a new standard known as 5G-I. We'll come to that in a later slide. So this is one of the reasons that has seen a little bit of that has resulted in a little bit of delay for 5G to be implemented in India. Anyway, so this figure basically shows the standardization for 2020 launch and beyond worldwide basically. So around 2010, the research started on 5G, and I was fortunate enough to work on 2 European Union projects known as Horizon 2020, and both were on 5G. So from around 2013 to 2017, I worked on those projects, and I was also involved in the research, prototype, and trial of this 5G standardization. So 3GPP basically releases certain documents around every year. Okay, every year, couple of years, they keep on releasing certain documents. So around 2010, 2011, release 10 was released, which are basically standardization documents. Then came release 11, then came release 12, then came release 13. If you look here, you'll see that in the meantime, LTE was also being modified and LTE was also evolving. So LTE basically became LTE-A, LTE Advanced Phase A, then became LTE Advanced Phase B, then became LTE Advanced Phase C. So by 2020, it was expected that it means 3GPP now has stopped. Release 16 will probably be the last time that 3GPP is going to put forward certain modifications for LTE. After this, everything will be release 17, 18, 19, everything will be for 5G only. So around 2017 to 2016-17, the first release of 5G specification was provided, and it was the year 2018. In release 15, basically the first release of 5G specification was given. And the second release of 5G specification was given in release 16. So this is how the 3GPP works. So you may have heard about 6G also. So 6G now is in the state of research, prototype, and trial. So now LTE's support will be over. So 5G will continue to develop like this for the next 10 years. And in the meantime, 6G will be basically in research, prototype, and trial mode. So that in 2030, we are able to see 6G, that is beyond 5G. Okay. So this is something similar. That shows what is beyond 5G, like release 17. So basically, continue expansion to new verticals, deployment use cases, new spectrums, those kind of things. 23 and beyond. Okay. So, as I was explaining, so the three main verticals of 5G will be EMBB, URLLC, and IoT or MMTC, massive IoT or MMTC. EMBB will encompass fixed wireless access, smartphones, then augmented reality, 3D, 8K video, all those things. Industrial IoT or URLC will cover all the mission critical applications like autonomous vehicles, smart grid, factory automation, etc. Similarly, MMTC, all those sensors, smart cities, smart logistics, smart metering, all those things, smart homes, etc. Okay. So 5G will enhance existing use cases and expand to even new use cases in both consumer and IoT markets. Okay. So it is not just a new generation, but a completely new kind of network. Okay. It is scalable, edgeless, and unified at the same time. It is going to connect new industries and devices, and it is going to enable new services, and it is going to empower new user experience. So this is 5G in a nutshell. So if you have any question until now, you can ask me, as I will now next move on to the next part of the presentation.
Dear participants, if you have any question, you can ask.
Until now, what we have covered, if you have any questions based on that, you can ask. If not, we'll move on to the next part.
Yes, most probably there is no question, sir. You can move on.
Okay.
Okay, sir.
So as you can see here, or as I have been explaining, you must have understood by now that 5G, it will cover most of the, it will take into consideration many devices. It's going to accommodate billions of devices. So the, sorry, the software that was presenting, it crashed. Just give me a moment. I'll just reopen it.
Okay, sir.
So the natural question is, how will 5G accommodate billions of devices? There is a formula known as the network throughput formula. Asher, you can mute yourself.
Yes, sir. Yes, sir.
Yeah. So there is a formula called the network throughput formula. And the formula basically looks like this. So throughput is equal to cell density times the average times the available spectrum times the spectrum efficiency. So what this formula basically says is that, so our goal anyway, one of the goals is to increase throughput, right? One of the goals is that we are hungry for data. We want as much data as possible. That means we want more bits per second per kilometer square. Now, how you can increase this throughput is that you can increase this throughput by increasing either of these three things. Either you go with this, either you increase the cell density, or you increase the average spectrum, or you increase the bits per seconds per hertz per cell, that is spectrum efficiency. You can do either of this, or you can do two of this, or you can do all of this. Whatever is feasible, at that point, you can do anything that is possible for you. So, but the target should be to have the maximum throughput possible. That is the goal of all communication engineers, right? We want to increase the most of the papers and research papers that you see. You will see that we are plotting average data rate. We are trying to increase this. We are trying to increase this data rate as much as possible, right? So that is the goal. Now, as I was saying, that you can either increase cell density, you can either increase available spectrum, you can either increase spectrum efficiency, or you can increase all of them, two of them, whatever is feasible at that point, you have to decide. Now, cell density you can increase through network densification. That means through heterogeneous networks, you can increase the cell density. Now, available spectrum, as you know, so if you might have heard already that the 5G spectrum is divided primarily into two parts. One is known as the FR1, other one is known as the FR2. What is FR1 is frequency range 1 and FR2 is the frequency range 2. Now FR1 is basically the frequency that is less than 7.25 gigahertz, or sometimes known as sub 6 gigahertz. Okay, so less than 7.25 gigahertz is the FR1, sometimes also referred to as sub 6 gigahertz. We are going to look in details about into this spectrum that are available. For now, just understand that FR1 is 7.25 gigahertz or below, and FR2 is basically above 24.25 gigahertz. That is the millimeter wave bands. That is the millimeter wave bands. Okay, so in the millimeter wave spectrum, there is abundance of spectrum available. So that is the FR2 spectrum. Then the another way is to whatever currently. So basically now we mostly operate in the sub 6 gigahertz. So we mostly operate in sub 6 gigahertz. So another way is to increase the spectrum efficiency of the current spectrum bandwidth that you are in. How you can do that? You can do that either by using massive MIMO, you can do that by using full duplex communication, you can do that by using non-orthogonal multiplexing access, RSMA, DSS, dynamic spectrum sharing, etc. So these are some of the techniques that you can use to increase the spectrum efficiency of a network. Now, full duplex communication here is highlighted, is in bold, because today's talk is about full duplex communication. Now, this is a slide that shows the target spectrum around the globe for 5G. So,
Hello, who is that person who are removing me and speakers? Please, if you are doing by mistakenly, please take care of it.
is my screen visible?
Yeah, yes, sir, it's visible now.
Yeah, so what I was saying is that so this is the 5G target spectrum that is being considered around the globe. You can see that a huge
Hello, Tasha sir.
Are there many internet issues or what? Am I audible?
Yes, sorry
Yes,
for the
sir.
interruption. Yeah, yes, sir. Not audible only, sir. I think.
My screen is visible now.
Yes, sir. The screen is visible.
Yeah. Okay, so basically the 5G target spectrum around the globe, you can see it here on the screen, and you will see that the chunk of the spectrum also considers the sub 6 gigahertz around the world. So sub 6 5G is a very important part of 5G. Not only so, you must hear on a lot of blogs or articles that millimeter wave 5G is the real 5G, but it's not exactly the case. Sub 6 5G is also going to uh, make 5G what it has been promised. Okay, and actually, a lot of mobile phones today that are coming, they are coming with sub 6 5G only. So the reason for that is that though this frequency range 2 or the millimeter wave, it has abundant unused spectrum, transmission in millimeter wave frequencies, they are plagued by severe attenuation. And this is due to various environmental factors. And as a result, this millimeter wave transmission in millimeter wave band, they require highly directional transmission. And also, one more thing is that since the frequency range is different, frequency is very high, you will need a significant overhaul of the existing wireless infrastructure to be able to implement the millimeter wave 5G. And as a result, the sub 6 gigahertz spectrum or the FR1 is still the gold standard for transmission. Okay. Unfortunately, it is extremely crowded. So if you look here, this part is the sub 6 gigahertz 5G, and a lot of countries, including the US, Canada, Europe, Britain, all those countries, including India, they are considering sub 6 gigahertz 5G. So one problem with sub 6 gigahertz is that it is extremely crowded. So there is one technology that can help to mitigate this problem, and that technology is full duplex. Basically, with full duplex communication, it is possible to double the available spectrum, whatever you have. So any technology that offers a way to more efficiently use the existing spectrum at a time when operators are trying to secure more spectrum for 5G is definitely worth a closer inspection. Okay. So now we enter into our today's primary topic, that is full duplex communication. So as the term has duplex in it, so you might ask, what is duplexing? So duplexing basically refers to the mechanism of dividing a communication link for the uplink and downlink. For example, if you have a base station like this, there is a user that is trying to uplink towards the base station. There is another user that is trying to get some downlink information from the base station. Then if you divide this communication, this uplink and downlink, into two parts, that is known as duplexing. So until now, basically, we primarily use two types of duplexing schemes for cellular systems. One is known as FDD, or frequency division duplexing. Another one is known as TDD, or time division duplexing. We're going to look at what those two things are. And both FDD and TDD, they are known as half duplex communication. Why? We're going to just speak about it in a bit. So let's first talk about TDD. Okay. So currently, basically, as I said, most systems work either on TDD or FDD. So what is TDD? Basically, you are dividing the time into two parts. So if you look at this figure, what you can see is that the transmission of uplink and downlink, they are happening at the same frequency, but at two different times. The uplink is happening in T1, the downlink is happening in T2. So basically, you are dividing the time into two slots while transmitting in the same frequency. That is TDD. Now, what is being wasted here? You're wasting time resource, because at any particular time you can either uplink or you can downlink, and you might also need some switching interval between the uplink and the downlink. So basically you are wasting time resources. Okay, that means latency is creeping into your system. Next is FDD. So what is FDD? So in order to reduce the latency, let's say, what you do is that you now utilize the entire time. That means in the same time you are transmitting and receiving as well in the same time. But how you are splitting the communication is you are splitting it in frequency. That means for F1, you are only doing the uplink. For F2, you are only doing the downlink. Let's say F1 equal to F2, and here you had the entire bandwidth as B. So basically F1 equal to F2 equal to B over 2. Let's say. Okay. Now, if you have some, you might also need some guard bands. You might also need some guard bands. Then this F1 equal to F2 even goes below B over 2. So what you are wasting here? You are wasting frequency resources. So for TDD, you are wasting time resources, and for FDD, you are wasting frequency resources. So now enters full duplex communication. Now, full duplex communication is a communication where you can do simultaneous transmission and reception in the same frequency band. That means now uplink and downlink can happen in T1 F1, and sorry, the uplink can happen in T1 F1, and the downlink can also happen in T1 F1. Same time and same frequency. Okay. Now your natural question should be to ask me, so if full duplex, so okay, before you ask the question, before that, since you are now utilizing the entire time and the entire frequency, so you are actually utilizing the entire B bandwidth. So that means you are utilizing 2 times the bandwidth. So you can achieve up to 2 times the throughput without any additional power or bandwidth. That means no wasted time or frequency resources. So now if you see, for even a small megahertz of bandwidth, people are operators are fighting like crazy. They go on sale for lakhs and crores of rupees. If I tell you that whatever you have today, so suppose 1 gigahertz bandwidth you have today, just by implementing full duplex, you can make it 2 gigahertz. You don't need any more bandwidth, so free. You don't need any more transmit power, so free. If I tell you that you can double it, how lucrative that sounds, right? So now let's come to the question. The question is, if full duplex is so good, so lucrative, why hasn't it been implemented yet? What has stopped it from the current implementation? What has stopped it from even being considered for too realistic for 5G? So it was considered as too futuristic for 5G because 5G is in 2020. So it was considered as too futuristic. So it is a beyond 5G technology. So what are the reasons? The primary reason is since the downlink, is happening at the same time and frequency as the uplink. So this downlink transmission of this base station is interfering with its own uplink transmission. That means the signal that is emitted from the transmitter antennas. So these are the transmitter antennas, right? So the signal that is emitted from the transmitted antennas of the base station is also received at the receiving antennas of the same base station. So this is known as self-interference. And this self-interference is so bad, this self-interference is so high that it completely saturates the front end of the receiver, and so much that whatever is received here is nothing but junk. So this is a very big issue. There's another thing called the co-channel interference, a slightly lesser but prominent issue. So when the uplink users are transmitting at the same time and frequency, the uplink users will also interfere with the downlink users.
Hello, sir.
Yes.
Sir, once again that repeat, sir, that interference.
So basically what happens is that, so this full duplex communication, the transmission and reception happens in the same time and frequency. So this is an example where a base station is downlinking some information to the downlink users. And at the same time and same frequency, some uplink users are also transmitting information to the base station. Now, what the base station has to do is that base station has to decode whatever information this uplink users has sent. Right, the base station will decode it here. This is the receiver of the base station. Now, whatever information is transmitted in this direction, since the base station is a compact base station, it has its transmitters here, its receivers here. So whatever is transmitted in this direction will also be received in the receiving antennas, because these are the receiving antennas, these are the transmitting antennas. So apart from receiving this user's signals, it will also receive whatever it was transmitted from this direction. And this because this is coming from some distance, and this is where this self interference is very close. This SI basically overpowers this signal. As a result, this signal cannot be decoded at the base station. This is a very fundamental issue of full duplex receivers. We're going to look into now, the next few slides are going to explain this only. You will be able to understand it in more details. So we have to do something to basically cancel this self-interference. This self-interference, we have to do something to cancel it. And this is a tricky part. Until 2010, there was almost non-existent literature on this. In 2010, a group in Stanford, they basically managed to cancel the SI. After that, several other groups have proposed various techniques to cancel the SI. And presently, there are more than 1,500 published papers on these topics. And currently, one of the hottest topics in communication field. However, it's still not perfect and still requires a lot of work. Means I myself have most of my publications of around more than 30-40 publications are on full duplex itself. So you can imagine that still a lot of work is required before full duplex can be implemented in practice. And that is the reason full duplex is a 5G and beyond communication technology instead of 5G technology. So we are now going to go a bit more details on this full duplex communication. So here are two example scenarios. One of them is the cellular system scenario that I just explained. So there is a base station, let's say a full duplex base station that is transmitting some information towards a downlink user, let's say, and receiving some information from an uplink user, let's say. And this downlink transmission is creating the self-interference at the receiver. So this is one problem. Next is a point-to-point system where you can relate it to a device-to-device communication or an IoT communication or a machine type communication, where there are two full duplex nodes trying to communicate among each other. So this is the downlink and this is the downlink as well. And so basically they're in a point-to-point, let's say, let's not call it downlink communication, and it's an X channel. So let's say this is the transmitter, this is the receiver, this is the transmitter, this is the receiver. Okay, so now this transmission will interfere with this receiver, this transmission it will interfere with this receiver. So that's how significant this SI is. This is the SI here and this is the SI here. Okay. Now let's go back to the cellular system example and let's see what this how we can quantify this self-interference. So let's say that this transmitter is transmitting some symbol, let's say x1 t e to the power j omega t, and the receiver is receiving some information x2 t from a uplink user. Okay. Now the self-interference, this SI, is much greater than the received signal of interest. Means you want to decode x2, but this x1 ej omega t is much stronger than this x2. Basically, the self-interference overpowers the signal of interest by around 80 decibels. Okay. So you have to cancel it. So how do you do it? In theory, what you can assume is that this part is the known part. This part, the base station is transmitting, so it is known. So you can so what you have to do is that, so you know this, you have to estimate that this is known. You have to assume that this is known because the base station is transmitting it. You don't know this because this is the wireless medium, wireless channel. You have to estimate this properly, and this self-interference power will affect the receiver through this multiplicative noise or the channel, So if you can estimate the SI channel properly, then you can easily cancel this term. Right? Once you cancel this term, you can claim that your system no longer has any self-interference. Now that is a solution in theory. But in practice, that is not the case. Why? Why it is not the case? The reason is that estimating this channel is not very easy. And estimating this channel is not easy when there are some scatterers around. So this channel is not just this channel. This signal may come via reflection from these scatterers. This signal may come via this scatterer to the receiver, from this to here. So there may be, so this wireless environment is not static. So wireless environment, in order to predict the channel state information is not very easy. So getting rid of this is not very easy as well. Though in theory it is possible, in practice it is not very easy. So what happens basically is that, again, the same example. So the received signal, let's say is Y1T. It is, as I said, so this signal will be received here after the multiplicative noise or the channel as this. So this is the signal of interest, and this part is the addition of self interference. This part is the addition of self interference, right? Now this is received at the receiver chain. After that, it passes through the ADC. After it passes through the ADC, it will be converted into the symbols or bits that you had generated, that you wanted to transmit. So what happens after this received signal that has been adulterated with self interference passes through the ADC? So you can see here, this is the signal of interest. The red one is the signal that you have received. The blue one is the self-interference. Now, ADC means you have to do the quantization. So after quantization, it looks like this. After quantization, it looks like this. And basically, where is your received signal? If you remove this, what is left is this. This is nothing but quantization noise. You cannot decode this from this because there is no resolution to decode it. There is only 1 to 2 bit of resolution here. This cannot be decoded by the receiver. The receiver at least needs 6 bits of resolution. Receiver at least needs 6 bits of resolution, and here only 1 or 2 bits of resolution you can find. That's it. So this is nothing but quantization noise, and basically why you have encountered this is because of the large SI over S. That means the large signal to interference over signal power is leading to a large quantization noise. So the strong self-interference, it must be mitigated before it reaches the ADC. That means you have to mitigate as much as possible in the analog domain itself. The digital domain after ADC, it is a digital domain. So you have to convert, or you have to cancel the SI as much as possible in the analog domain itself to avoid large quantization noise. So how much interference is to cancel? That should be your next question. How much SI you have to cancel? And once you know how much SI to cancel, next you have to know how to cancel it. So the first step is, let's quantify the SI, or let's quantify the self-interference. So this is an example that we are going to consider to quantify the self-interference. I'll just grab a glass of water. So this is an example. If you so on the left hand side is a small cell scenario, and on the right hand side is a Wi-Fi scenario. Let's consider that both the small cell scenario and the Wi-Fi scenario are operating in full duplex mode. Okay, and basically the transmit power for the small cell scenario, let's say it is 20 dBm, and it's the same for both the small cell and the Wi-Fi. Now, since it's operating in full duplex mode, the self-interference due to the transmit power of 20 dBm that it receives is around 5 dBm for both the scenarios. The noise floor for the small cell scenario is around minus 100 dBm, and the noise floor for the Wi-Fi scenario is around minus 90 dBm. Now the received signal strength for the small cell scenario is minus 80 dBm. Also for the Wi-Fi scenario is minus 80 dBm. Now the question is, your interference power is 5 dBm for both the cases. Your signal receive power is minus 80 dBm. So there is no way you can decode it. There is no way you can decode the signal. So you have to cancel this PSI. How much cancellation you need? You have to bring the PSI below the noise floor. The noise floor is minus 100 dBm. So how much cancellation you require? 5 minus 100 dBm, which is 105 dB. So for the small cell scenario, you need 105 dB of cancellation to bring the self-interference down to the noise floor. Similarly, for the Wi-Fi scenario, you need 5 minus 90, that is 95 dB of SI cancellation to bring the self-interference down to the noise floor. Okay. Now, let's say you didn't do the SI cancellation. What would have happened? For the small cell scenario, what would be your SINR? Your SINR would be, this is your signal of interest. So minus 80 minus 5, which is minus 85 dB SINR. For the Wi-Fi scenario, your SINR would be also minus 80 minus 5 minus 85 dB. Now, can your receiver decode your information at such SINR? Obviously no, right? So receiver is useless at such SINR, that is minus 85 dB SINR useless through the system. That means SI is dominant over noise. So SI cancellation is required in order to enable full duplex receiver. So basically, for the small cell scenario, your cancellation should be greater than 105 dB, so that the SI's self-interference cancellation is below the noise floor, that is minus 100 dBm. Similarly, for the Wi-Fi scenario, you need around 95 dB cancellation to bring the SIC to around minus 90 dBm. Okay. And if you manage to do that, then noise is dominant over SI, then you get a very good SNR. Okay. And how much? Let's say you manage to do the cancellation of 105 dB of SI cancellation, then your SNR becomes minus 80 minus 100, that is 20 dB SNR. And for the Wi-Fi case, minus 80 minus 90, that is 10 dB SNR. Okay. So 20 dB SNR, very good. 10 dB SNR, also good for the receiver. Okay. So in a nutshell, large amount of SI cancellation is required to mitigate the self-interference or to bring the self-interference to below the noise floor. So for the small cell scenario, you need around 105 dB of self-interference cancellation. And for the Wi-Fi scenario, you need around 95 dB of self-interference cancellation. Now with the network densification, if you remember in the network throughput formula, one of the things was network densification. So there is a possibility that once you make the network more dense, you are actually reducing the cell size. You are actually reducing the diameter of the network. So what happens is that you are actually, by reducing the dimension of the network, you are also reducing the transmit power. Okay. So with network densification, the transmit power tends to reduce. So basically, if the transmission power is less, the self-interference is less. So the self-interference cancellation required may also be reduced, assuming that the noise floor is the same. Okay. Now the gain of full duplex over half duplex, it will depend on the amount of self-interference cancellation that you can achieve. Okay. So basically for half duplex communication, the performance depends basically on the noise floor only. And for the full duplex communication, the performance depends on the self-interference and the noise floor both. So next, we are going to do a comparison of full duplex and half duplex communication as a function of the amount of self-interference cancellation. So let's consider the same example of small cell, let's say. And so this is a TDD system, half duplex, TDD half duplex system, where you can see that the transmit power is 20 dBm for both the cases. Let me just move ahead a little bit. As you can see here, for the half duplex case, it depends on the noise floor. So you once you transmit at 20 dBm and receive the signal at minus 80 dBm, and the noise floor is minus 100 dBm, so you receive a SNR about 20 dB. But for the full duplex case, it is interference dominated, self-interference dominated. So the SINR is minus 85 dB without any cancellation, without any SI cancellation. So the reception rate basically for the full duplex case is 0 bits per second as compared to the half duplex case. Okay, so let's say the transmission rate is TX bits per second per hertz, and the reception rate is RRS bits per second per hertz. Let's say the transmission rate for the full duplex is the same, but at the receiver, without cancellation, the full duplex is going to have 0 bits per second per hertz with this kind of SINR. Now, if you do manage to cancel that SINR, that self-interference, then things changes drastically. So let's say the SINR of full duplex is also 20 dB with around minus 85 dB of cancellation. Sorry, with around 105 dB of cancellation, the SINR is around 20 dB. So in that case, the SINR, there will be some rate that is received by the full duplex, and let's denote it by this term RRSFD. Now, basically what happens is that the half duplex system, it requires a TDD system, it requires 2 time slots to transmit, right? So whatever rate you have to divide it by 2. Now full duplex system, once the cancellation is done, the reception rate is using basically the entire rate that is available. That is information theoretically possible for the system. So this entire rate will be RRX. So in this way, what you can see is that the full duplex RRX is 2 times the half duplex RHD. Let's look into it a bit more in details with this curve. What happens is that, let's say this is the half duplex rate, which is RRX over 2, as we just saw here. Now, the 2 times rate or RRX is given by this curve. Now, full duplex, if SI cancellation is not done, we saw that the rate is 0. Once we start doing SI cancellation, you see that the rate keeps on increasing. And once you do this 105 dB of cancellation, you actually achieve 2 times the rate. You actually achieve this 2 times gain over half duplex. In between, there is a crossing point between full duplex and half duplex. This is usually around 50 to 70 dB sometimes. And basically, if you cannot do SI cancellation beyond this point, there is no point using a full duplex communication. It is better to use half duplex over full duplex, but in this region, it is better to use full duplex over half duplex. As you can see that the gains that you achieve beyond 105 dB is around 2 times, and after that you are not going to receive any more gain, because that is the information theoretically possible reception rate that is possible. That is the Shannon's, that is provided by the Shannon, and so after that it is not possible, but 2 times increase in capacity is possible. Now, how do you achieve those self-interference cancellation? So you can achieve this self-interference cancellation through a combination of antenna cancellation, analog cancellation, and digital cancellation. Okay, what is antenna cancellation? Basically, antenna cancellation, two transmit signals interfere destructively at the receiver antenna. You place the antennas in such a way that at the receiver, the signals will destructively interfere. Analog cancellation is basically the one that is done before it reaches the ADC of the receiver. That means before you digitize the SI, you have to cancel it. And digital cancellation is basically the cancellation in the digital domain. And antenna cancellation can compound to around 20 dB of cancellation. Analog cancellation can provide you around 50 dB of cancellation. But remember, we need around 105 dB of cancellation to perfectly achieve this 2 times throughput. So analog and antenna both can give around 70 dB cancellation. So what is left? Around 30 to 35 dB is left, and this much you have to take care in the digital domain. Okay, so we are going to discuss this now. Now each of it has their advantages and disadvantages. So the advantage of all analog self-interference cancellation is that there is no quantization noise, but it is very difficult to implement due to the large amount of cancellation that is required. 105 dB in the analog domain is very, very difficult. Now, if you go all digital is again not possible, as we saw that there is a very high quantization noise, and you will end up with no benefit over half duplex even if cancellation is large because of the quantization noise. Now, the solution is hybrid. That means hybrid analog and digital. So you take care of certain parts with analog and certain part with digital. So if you see here, so this figure is basically the full digital. So basically even worse than the half duplex case. And this figure is with the full analog. If you can do it, very good, but it is not possible in reality. And this is the figure where you do it over through hybrid analog and digital. And you see that you are not going to get as good a performance as the 2 times throughput promised, but you will get much better throughput than half duplex communication, and you will definitely be able to increase the spectrum efficiency of the network. Okay. So this figure is basically a full duplex transceiver, and you can see that there are a bunch of transmit antennas, there are a bunch of receive antennas, and this is the transmit chain, this is the receive chain, this is the digital domain part, this is the analog domain part. Now, as I was saying, you can do antenna cancellation in the antenna domain, then you can do some analog cancellation in the analog domain, then you can do some digital cancellation in the digital domain. And this self-interference, as I was mentioning before, basically these transmit antennas are the signals interfere here. So you have this direct path SI, this is the direct path SI, then you also have the reflected path SI. You also have the reflected path SI. The direct path SI and the reflected path SI forms the entire total SI. Okay. So now let's look into what antenna cancellation is. So antenna cancellation looks something like this, where you can see that there are two transmit antennas. Basically, they are spaced in such a way that the receiver is spaced in such a way that it is d distance apart from the transmit antenna 1 and d plus lambda by 2 distance apart from the transmit antenna 2. That is, it is lambda is the wavelength that it is placed at 1/2 wavelength offset. So under such a setting, what happens is that this receiver receives signals from this receiver, receives signal from this antenna, and both antennas are transmitting the same information, and the two transmit signals basically interfere destructively at this receive antenna. Okay, how it achieves this? By having one 1/2 wavelength distance offset between the two transmit antennas, and this destructive interference, it cancels around 20 to 25 dB of self interference. Next is the analog cancellation. So this is an example of an analog cancellation where a balloon transformer is used, or a balanced unbalanced transformer. So basically what happens is that the transmitter is transmitting certain information, right? And so the same information is also passed through a balloon, that is the balanced unbalanced transformer. And this is a negative signal. This is a negative signal which is which after taking care of the attenuation and delay of this of the transmitted signal, you sum it up with the received signal, and this is how you cancel them. So basically, you are cancelling the self interference by making the self interference negative, and then adjusting the attenuation and the delay, and then just adding it to the actual SI. And this way you can get around 40 to 50 dB of self interference. So as I was telling before, this antenna cancellation and analog cancellation can give you around 70 dB of cancellation, and the rest is left for digital cancellation. And the rest of the self interference is known as residual self interference. And this persists due to several factors like channel estimation errors, transmitter/receiver impairments, or hardware distortions. So because basically our hardwares, they are not ideal in nature, so it is so these impairments or distortions, they also create they also have a big role in not in us not being able to cancel the SI fully. And so depending on the strength of this residual self interference, the optimal transmit strategies that are there in literature for half duplex systems, they are far from optimal for full duplex system. Okay, so this residual system, you have to handle it well to actually exploit the benefits of full duplex wireless communication. And so how do we do it? We do it through the design of transceivers. Transceivers means beamforming matrices, power allocation vectors, and we do it in the baseband. We do it in the baseband, and we also take into consideration the hardware impairments, that is the limited dynamic range caused by the non-ideal amplifiers, oscillators, the DACs or the digital analog converters, and the ADCs in the design of this transceivers. So our main work basically revolves in this digital domain, this design in the baseband, that we design this optimal transceivers. Okay, next we're going to move into the next part. If you have any questions, you can ask me now before we go into the application scenarios of full duplex radios. So this was a brief idea about how what self interference is in a full duplex communication, and how you can take care of the self interference in practice. Okay, if there are no questions, then I'll keep continuing.
Yes, sir. Yes, there is no question are coming. So
Yeah.
it can move on, sir.
Yeah, sure.
Okay, sir.
So basically, the full duplex deployment scenarios, there are various deployment scenarios that you can find in literature, and a simple deployment scenario is a two-node topology. And this two-node topology basically means that, as we saw in one of the previous slides, is the point-to-point communication where both the nodes are operating in full duplex. So since both the nodes are operating in full duplex mode, so both the nodes, they will encounter self-interference. Okay. And so some deployment scenarios or examples are Wi-Fi direct, Bluetooth, then 5G also is there, then device-to-device communication. You can also consider Wi-Fi and small cells under this node topology. Another one is the three-node topology, and this is the example that I was considering more in explaining the full duplex networks. This is the topology where you see that there is a central node which is operating in full duplex mode. This can be considered as a cellular base station. There are some half duplex nodes as N1 and N2, which can be considered as uplink and downlink users. So deployment scenarios for such three-node topologies are cellular systems, that is 5G, gigabit LTE, relay systems. There can be some access point devices also under small cells and Wi-Fi scenario. Now, this both this two-node topology and three-node topology can be extended to multiple nodes. So two-node topology can be extended to up to k nodes and become an interference channel. And the three-node topology, also the multiple half duplex node can be extended to up to k nodes. And cells, if you consider this as cells, this is one single cell system. It can be extended to multiple cell systems as well. Okay. So next is some other applications scenarios of full duplex. One of the applications is physical layer security. Now, what is physical layer security? Basically, it is how you protect a device in the physical layer. So here in this example, if you see, you can see that full node 1 is full duplex and node 2 is also full duplex. And node 1 is trying to send some data to node 2, And whatever information is being transmitted, there is an eavesdropper which is trying to listen to node 1 through this channel. Now, what node 2 can do is that at the same time as it is receiving as the information from node 1, it can also transmit a jamming signal towards the eavesdropper. So this is all happening in the same time and same frequency. Now, this is not possible in half duplex mode, because in the half duplex mode, this node can either transmit or receive. It cannot do both. Now it is receiving the information from node 1 as well as transmitting the jamming signal to the eavesdropper. So this is the advantage of full duplex communication, that is security through jamming. So what it basically does is that it basically neutralizes this eavesdropper, and the eavesdropper can no longer hear to what node N1 has to say. So N1 security is enhanced. Next is the application in cognitive radio. So cognitive radio, you must already know that it's a form of wireless communication in which a transmitter can intelligently detect which communications channels are in use and which are not, and instantly move into vacant channels while avoiding the occupied ones. Okay. Now, the advantage of full duplex cognitive radio is that a full duplex cognitive radio can transmit and sense the transmission status of other nodes. And this helps to combat several problems, not only in the file layer, but at the MAC layer also, such as hidden terminals, large decays, large delays, and congestion as well. Now, this is an example. Let's say you have a half duplex cognitive radio where you have some primary transmitter communicating with primary receiver, and the secondary link is trying to find out the spectrum holes when it is not transmitting. So what happens is that it can either transmit or sense. It cannot do both. So while it is transmitting, it cannot sense, and while it is sensing, it cannot transmit, since it is in half duplex mode. So while it is transmitting, the primary link is back, and there is a delay since it cannot sense and transmit at the same time. So there is a delay for detection of the collision. Okay. So that secondary transmitter, since it cannot listen while it's transmitting, there is a delay there of detecting this signal power that the primary link has entered, and therefore there is a collision. But the advantage of half duplex is that while the secondary link is transmitting, it is also sensing. It is transmitting and sensing at the same time. So it is transmitting here, and it is sensing here, right? So it is transmitting and sensing at the same time. So what happens is that as soon as this guy enters back and takes over the spectrum, it has come to know. So it has stopped the transmission. So the collision is much less or even not there also. Okay. That means with full duplex, you can discover your neighbor in a much better way. So it is a boon in the realm of cognitive radio. Another application is electronic warfare. Now, what happens in today's war scenario is that most of it is digital, and most of it is won based on information. So let's take an example of two teams that are involved in war. Let's say team A is equipped with full duplex radios in all their systems. Team A is equipped with full duplex radios, and team B, let's say, is still in half duplex mode. Okay. So considering this example, visualize this example, then let's see what are the scenarios that are possible. Look at the scenario A. So as I mentioned, team B is only half duplex, and team A is full duplex. Now team A, since it is full duplex, what it can do is that it can jam the signal. So for example, let's say team A's transmitter is transmitting some information to the receiver, to its receiver, and this receiver is operating in full duplex mode. So at the same time as it is receiving the information from the transmitter, it is also jamming the receiver of the team B. Now, what was team B trying to do? Team B was trying to receive the information from its own transmitter. For example, if the situation is a war-like scenario, if the enemy cannot communicate among themselves, then the war is already won, right? Because here what is happening is that while team A, the transmitter is providing all the information to the receiver, in team B, due to this jamming signal, there is no exchange of information between the transmitter and the receiver. Next example is here, where the team B, there is a receiver which is trying to intercept the communication between team A's transmitter and receiver. So again, team A's receiver is operating in full duplex mode. So what it can do is that it can send a jamming signal so that the team B's receiver cannot intercept their communication. So this is known as jamming against interception. This the A example is known as jamming against communication. This is known as jamming against interception. Next is now team B. What it is trying to do is that, sorry, team A. Now let's say team A's this node, transmitter node, also is operating in full duplex mode. So this team A, now what it can do is that it can also intercept this communication. Whatever this team B's transmitter is transmitting to the receiver, it can intercept this communication and simultaneously pass this information to the receiver of team A. This is known as interception and communication. Simultaneous interception and communication. Now let's say team A's both radios has full duplex communication. Then it is like supreme power. It can not only intercept whatever team B is transmitting, it will also jam the signal of team B. So team B is totally incapacitated. Team B cannot communicate among each other, and all the information that team B is trying to communicate, team A already knows. And if you have information, if you know the information, let's say about the location of your soldiers, the location of your artilleries, let's say the team B is trying to provide this information, team A already knows, and the war is already won. You understand it, right? So this is the power of full duplex communication. So electronic warfare, in cognitive radio, improving the security, and many more, and many more. These are a few examples that I could put in this presentation, but there are many more examples that full duplex communication can give you. And so this is the reason that full duplex communication is such a hot topic today. Okay. So now we are going to look into a case study on how we can design a full duplex transceivers. Before that, we'll just take a couple of minutes break before we continue. So in the meantime, if you have any questions, if you can ask me. I'll just take a couple of minutes break and I'll be back.
Okay, sir. Okay, if you have any queries, you can directly interact with sir, or you can post your question in our WhatsApp group also. At the end of the session, we will try to discuss. कारण से বাবু কয় পার্সেন্ট হয়েছে রে?
Okay, so welcome back. Yeah. So next, now that we know what full duplex communication is and what are the implications, of implementing full duplex radios, so we might want to look into how we can implement full duplex radios, basically in the digital domain, as the case study that we're considering are for the digital domain only. We're going to discuss some optimization driven designs and also some data driven designs. Data driven designs means that the machine learning based designs that are currently in trend. So we're going to look into that as well. And since throughout the presentation, we have been speaking about both cellular networks and IoT networks. Basically, if you remember, we spoke about the two-node topology and the three-node topology. So the two-node topology basically it resembles kind of a cellular network, and the three-node topology resembles kind of a cellular network, and the two-node topology kind of resembles a IoT network. And this figure basically is an extension up to k-node topology. If you look into this figure, there are k number of nodes on the left hand side and k number of nodes on the right hand side, and there are two columns. And let's say we make this a little bit smaller for you to understand. Let's take this part, and so then this will look like this. So I basically is the ith node, j is the jth node, and 1 and 2 basically indicates the two columns that we are here, right? So this is kind of an interference channel, or referred to as a full duplex IoT network as well. So what is special about this network? Basically, we consider that all the nodes are MIMO nodes. That means multiple input, multiple output nodes. So it's a full duplex MIMO interference channel consisting of k pairs of IoT nodes. And as I mentioned that in the digital domain, we work primarily on the baseband. So all the signals mentioned here are defined in the complex baseband. So each pair is equipped with multiple antennas and exchanges information simultaneously in a two-way communication. And let's assume that the full duplex nodes in the IIIT link have NI transmit and MI receive antennas. And the goal is to design beamformers in the digital domain, considering that cancellation and the analog domain is already done. Now, first and foremost, we're going to look into the optimization driven design. Okay. So if you choose an IoT network, so one of the important things that you must consider is what is the performance criteria that you want to consider before designing. And some power minimization is a very important performance criteria for IoT devices. And the reason is that green communication has basically, you will see that green communication is everywhere. And because of the popularity of IoT, because they are devices that can support only limited energy supply, and with the promotion of this green transmission in 5G networks, that emphasizes on incorporating energy awareness in communication systems, it is always preferable to minimize the total transmission power consumed in the system or to maximize the energy efficiency, as compared to some rate maximization problem that you see a lot in literature. So since the transmission and reception in the full duplex IoT network operate simultaneously in active mode, so the full duplex network usually requires more energy than a half duplex one. So hence, if the transceivers are not designed properly, the power energy consumption of the full duplex system can be much higher than that of half duplex system. So some power minimization is a very considerable metric that you can consider, right? Since this is the MIMO, this is the MIMO device. So what how you can formulate the problem is, so V basically is the set of all precoding matrices. Okay, so you can minimize the trace of VV Hermitian, which is the total transmit power of the system. Now with constraints on the rate. Here, this optimization problem basically shows that, if you remember, there are k number of nodes and there are two columns. So the entire system has this number of nodes, right? And trace VIA means that individual node, the precoding, the trace of VV Hermitian for the individual node gives the individual power. Now, when you are summing up with all the nodes, that means that the total power of the system. So you are minimizing the total power of the system with constraints on rate for each node. There is a rate constraint at each node of RIA bits per seconds per hertz. Okay. Now, how do you solve this problem? Basically, you have to find a stationary point for the problem here. Okay. In order to do that, what you do is that establish the relationship between the achievable rate and the MSE matrix. Okay. Now, there is a well-known relation between the weighted sum rate and the weighted MMSE, and with that, you can achieve the relation between the rate and the MSE like this, where E is the minimum mean square MSE matrix of the IoT network. Now, you might ask me, why do we need the MSE? Why do we need to compare it with convert it to an MSE? First of all, this rate in its current form, weighted sum rate, is non-convex. Okay. Now, second, MSE-based transceiver designs, they have been considered extensively. Why? Because of its good performance and significantly reduced complexity. And the next is that the MMSE, or the minimum mean square error estimation, plays a very important role in approaching the information theoretic limits of the Gaussian channels. Okay, since we are considering Gaussian channels here. So when MMSC receiver is used, the MSC based optimization problems are equivalent to SINR, or the signal to interference plus noise ratio based optimization problems, since MSC is basically equal to 1/1 plus SINR. Okay. So therefore, the rate-based optimization that you see in literature using log to 1 plus SINR, they can be conveniently transformed into MSC-based optimization as negative of log to MSC. Okay. So when MMSC receivers are employed, basically the achievable rate of a user is written as the negative logarithm of the determinant of the MSC error covariance matrix, which is tightly related to the user MSC. So thus minimizing the MSC of a user maximizes a tight lower bound on its rate. So that is the reason this WSR and WMMSC relationship is exploited a lot, and you can convert this sum rate into MSC like this. Then the problem that you can you can reformulate it using the MMSC in this form. So this is the same problem P1, or the sum power minimization problem. Now it is under individual weighted MSC constants. Before it was under rate constraint. Now you have converted the rate into MSC. So it is under individual weighted MSC constant. So this is the MSC matrix of the node IA, where I can be anything from 1 to K and A can be anything from 1 to 2. And since this is, now we have converted it into a weighted MSC. So W are the weights, is the set of all weight matrices, and R is the set of all the receiver matrices. So V was the precoder matrices, you remember, and R is the receiver matrices that we have introduced now because we are using a MMSC receiver now. Now this problem P2, it can be shown that the gradient of the problem P1 and the gradient of the problem P2 are equal if the MSC weights W, they are chosen in this fashion. And since the KKT conditions of P1 and P2, they can be simultaneously satisfied with the choice of the above MSC weights, we can solve the problem P1 through solving the problem P2. Okay. Let's say if V bar, W bar, and R bar, they denote the optimal solution of the problem P2, then V bar is also the optimal solution of problem P1. Hence, we only need to solve problem P2, and which is convex. This problem P2, after converting it into weighted MSC, it is convex in each of the variables W, R, and V. Now, what we use, we can use a block coordinate descent method to solve P2. That means for fixed V and R, we can get the optimal W. Then for fixed V and W, now this W is this W. For fixed V and W, the optimal R is the MMSC receiver that you can calculate. Then for fixed R and W, you can calculate the optimal V, that is V bar. Okay, and you can obtain this by using a Lagrangian dual method. So basically, this problem P2 is not jointly convex over the optimization variables V, W, and R. And so this proposed algorithm does not ensure the convergence to the global optimal solution. Okay, they are optimal in each of the variables, but not on all of the variables. And because of the non-convexity of the optimization problems that we are dealing here, so we also need to choose a good initialization points to have the suboptimal solution with very good performance. And several reasonable choices you can find in literature, such as right singular matrix initialization, random matrix initialization, interference alignment initialization. There are many methods. So this algorithm, though, will converge to a stationary point for the problem P2. Okay. Now this is the convergence figure for this problem that you can see for two different types of initialization techniques. Now, how do you implement this algorithm in practice? So basically, at each time slot, The receivers feedback their direct and cross links to the central node based on the global CSI, often from all the receivers. Then the central node will first perform the precoding optimization to compute the optimal V, and then it will be distributed. This optimal V will be distributed to the transmitters of the IoT network for the MIMO transmission. Okay. Now, what is this central node? This central node can reside at any node in the network. For example, let's say if you have a smart home kind of system, which is controlled by a Amazon Echo kind of device, then this Echo can be a central node. If you have a Google Home device, that is Google Home can be a central node. If you have a smart TV, this smart TV can be a central node. Okay. In a dynamic environment, this scheduler can be adaptively elected among the eligible nodes in the network. And this election of this central node can be done based on the capacity of a node, the status of a node, and the location of a node. Okay. So now this problem was we solved this problem in this paper, in this transaction paper, and these are a couple of results for this paper where we see the some power comparison of full duplex IoT and half duplex IoT networks with respect to residual SI in the network. So the x-axis gives the residual SI and y-axis is the sum power. You see that when the so basically this is low SI, this is high SI. So when the SI is very high, then full duplex will require more power. And when the SI is cancellation is good, then full duplex requires minimum power as compared to half duplex systems. And the next figure on the right is basically the desired sum power with respect to the desired data rate. So you see that when the desired data rate increases, the sum power increases for both half duplex and full duplex systems. But throughout, you see that sum power of full duplex is less than half duplex system. So that means to achieve a particular data rate, full duplex will require less power as compared to half duplex systems. That means full duplex is more power efficient. That is what we showed in this paper. Okay. Next is a full duplex single cell scenario. This was the IoT scenario, and this is a full duplex single cell scenario. Now, full duplex single cell scenario somewhat will look like this. And you basically have a full duplex multi-user MIMO cellular network in which a full duplex base station serves multiple half duplex users. And these half duplex users are divided into two pools of uplink and downlink users. Now, since it is in full duplex mode, so the base station encounters this SI, and this uplink users will harm the downlink users through CCI or the co-channel interference. Okay. So again, the task is to design the beamformers in the digital domain, and you can design the beamformers in a way similar to the one that we just saw for the IoT case. Here, the one change is that we are trying to minimize the sum power. Here, we are trying to minimize the sum mean square error. Again, considering MSC, the reason is the same. The reason is the same because basically we could have maximized the rate as well, but we have decided to go with the MSC because when MSC receivers are employed, the achievable rate of a user is basically the negative logarithm of a determinant of the MSC error covariance matrix, which is commonly known. Basically, hence, minimizing the MSC of a user basically maximizes a tight lower bound on its rate. Okay. So instead of considering each design criteria such as the MSC and the mutual and the maximal mutual information in separate way, so here we are considering a unified framework that is minimizing the MSC and subject to certain power constraints. This is the power constraints at each uplink user, and this is the total power constraint at the base station. We solve this problem again similar to the previous problem where we cast the problem as a second order cone programming problem. And then like before, we form an iterative alternating algorithm, which is guaranteed to converge to a local optimal solution. Okay, so here are some results. Here are some results for the cellular system. Here are some results of the cellular system. And you see that again, you see some similar trends, but now since
we have the cellular network. The performance metric that we plot here is sum rate with respect to SI and sum rate with respect to CCI. Okay. So you see that the full duplex is better than half duplex when the SI cancellation is more than minus 50 dB, and the CCI attenuation also, when the CCI attenuation is very low, that means close to 0, then full duplex will outperform the half duplex systems. So that was a brief idea about how optimization driven designs work, and means you can go through many papers in literature, that is where you will see that optimization driven designs for beamforming for full duplex radios. You'll find many literature. You will also find many literature that I have written, and many literature that other authors have written, so you can go through them. Next is data driven design. And as you know, that the world is at a stage where everything is shifting towards AI and machine learning. So as communication engineers, if we don't embrace AI and machine learning, so we'll be left behind. Okay. And there, of course, there are advantages also of using AI and machine learning. For example, the algorithm that we just discussed, basically it requires iterative loops with complex operations to find the optimal beamform matrices. And this iterative loops basically slow down the computation speed and make it kind of unsuitable in real-time scenario. And this can be addressed by designing algorithms by virtue of machine learning. So this is another paper that we recently published, and this is basically on multi-layer perceptron based beamforming design for a simple full duplex cellular system. Basically, what we do is that we first design a multiple multivariate regression problem, and then we train an MLP or multi-layer perceptron to solve the problem. So here is a brief idea. You can go through the paper to get some more details. And the data that we generate, is again through the ODD method that we just discussed. Because that means the structurally the MLP based design is structurally based on the sum rate maximization problem, or for that matter, the MSE minimization problem. And then we solved repeatedly that ODD based problem to generate a data set forming a multivariate regression problem. And we use that data set to train a multi-layer perceptron, and that is employed a supervised learning scheme, and that we use to solve the associate regression problem. This is a gist about the data generation. Basically the ODD problem, we use CVX. CVX you might already know, which is the MATLAB based package for specifying and solving the convex problem that we have in hand. And the program is written on MATLAB. This is how the data is generated. And for the MLP, we use the Python. We use Python programming language. And the MLP regression class the neural network module of sklearn. These are some of the parameters that we choose to work on this MLP. So we trained the network on 900 training points, and after training, we validated the data with another 100 points. Okay, and this is some of the experimental results that we obtained by applying this MLP. So you can see that basically what we do is that we compare the MLP-based beamformer design for the with respect to the ODD-based design in terms of sum rate, and to show the gains of the inverted full duplex over half duplex system, we also consider the half duplex system, as you can see here. So you must note one thing, that since the MLP is trained based on the optimization driven design, its sum rate performance is not expected to be better than the optimization driven design, right?
However, from these figures, you can see that the MLP-based design can achieve near optimal performance for the embodiment full-duplex system when kappa beta or the transmitter receiver distortion or the self interference is below minus 70 dB. So below it, if you see that the MLP based design is almost close to the optimal design. So beyond that, you will see that beyond minus 70 dB, the residual self interference starts overpowering the system, which affects the performance of the MLP, as you can see in this figure. Okay. So why exactly? Because there may exist a problem underfitting when this transmitter receiver distortion is greater than minus 70 dB. Okay. And for the half duplex system, since there is no self interference involved, so throughout the range of transmitter receiver distortion or self interference, you will see that the MLP and the optimization driven design, they almost are close to each other. Similar kind of figure can also be seen for the CCI case versus SUMRIT. So in summary, I would like to note that 5G wireless systems are just about in the horizon. Okay, and technologies such as EMBB, enhanced mobile broadband, IoT, machine-to-machine communication, and complemented with intelligent data analytics, they are expected to drastically change the landscape of various industries. And 5G will support new technologies for both cellular and IoT, such as full-duplex transmissions will arrive in future releases of 5G. So with full-duplex, it is actually possible to double that spectrum apart from being power efficient. Okay. So the recent advent in interference cancellation techniques, as well as the evolution of silicon, it has actually enabled the implementation of complex beamforming algorithm at base stations and mobile devices, which has made full-duplex close to being reality. Okay. So this is the reason that full-duplex has recently attracted immense popularity beyond academia. Companies around the world are venturing into full-duplex radios like Kumu Networks, Lexstrom, GenXCom, etc. So good news is that for researchers in wireless communication, true 5G is still on the horizon. So this is the perfect time to start planning for its arrival. Now, this is a figure that I took from Qualcomm, and it's about the deployment status around the globe. And one of the missing points you can see here is that there's no India yet. And one of the reasons, as I was mentioning, is that why India is slightly behind is that India is implementing a different form of 5G, which is known as 5G-I. So 5G-I is developed by Telecommunication Standards Development Society India, or the TSDSI, which is Standardization Society in India. So this TSDSI's 5G-I standard basically aims to bridge the rural-urban digital divide in 5G deployment on the back of enhanced coverage. Now, TSDSI claims that it has it has found the support from several countries because it addresses their regional needs from a 5G standpoint. And luckily, in December 2020, the ITU completed the 3-year-long evaluation of 5G-I and accepted it as a global 5G standard along with 3GB's version of 5G. So we are expanding, and COVID is another reason that the spectrum auctioning and all those things have been delayed a bit. But we are expecting that soon, either at the end of this year or early next year, we will be seeing the spectrum auctioning for 5G in India. Okay. So here are some future research directions for full-duplex radios, because and I have highlighted some of the machine learning based full-duplex radios and articles only because over the past 2 years, machine learning has been widely investigated and applied in communication. And
being an editor of IEEE transition on green communication, I also expect that soon rather than later we'll have many more special issues on machine learning for full duplex radios and wireless communications in general. This is some of the articles that I have chosen. You can look it up. I'm sure you will get a very good idea about how machine learning can be implemented in them. And in most of the articles, the data-driven design example that I've shown, they go in the similar way. Basically, they solve the optimization problem, create the data set, and then apply a neural network kind of a framework on top of that to train the network and get the desired results. So that's it from me. So thank you everyone for patiently listening to this long talk. So some questions I will take now. And before concluding, so there's a common question that people usually ask me. So that is 5G available now? And the answer to that is yes, 5G is already here. And in many countries, it has already been deployed. Global operators have started launching new 5G networks since 2019. Also, all major phone manufacturing companies are commercializing 5G phones, starting from the highest end Apple iPhones, Samsung phones, then even the mid-tier phones, they're coming with 5G now. Now, 5G has been deployed in 60 plus countries and counting. We are currently seeing much faster rollout and adoption as compared with 4G. We consumers are very excited about the high speeds and low latencies. Okay, but as you must already know that 5G goes beyond these benefits by also providing the capability for mission critical services and enhanced mobile broadband and massive IoT. In a nutshell, it is hard to actually predict when everyone will have access to 5G. But in India, we soon expect that we expect to see some momentum of 5G launches in its first year. That means this year or the year later. And yeah. Another question that I often get is that do I need a new phone if I want 5G? And the answer to that is unfortunately yes. You'll need to get a new smartphone that supports 5G if you want to be able to use the 5G network. Okay, and currently most of the 5G smartphones are powered by Snapdragon 5G mobile platforms. Even the Apple iPhone that supports 5G, it is the Snapdragon platform. MediaTek has released its chip known as the Dimensity chipset, which is 5G compatible. And there may be some other new mobile phones also that are designed to support 5G, and multiple carriers across the world support the 5G wireless network. And as the 5G rollout timeline progresses, more smartphones and carrier subscriptions will be available as the technology and along with the compatible devices become more of a mainstream. Anyway, so thank you all for patiently listening to this talk on 5G and beyond wireless communications and the role of full duplex in it. So with that, I'd like to conclude my presentation.
Thank you. Participant, if you have to the sir lectures, you can ask. Sir will answer definitely.
Yeah, so with that, I'd like to conclude my presentation. If you have any questions, you can ask me now. Thank you.
Yes, any question from participant side? You can mic. Okay, there is no question, sir.
Okay, no issues. So in that case,
Hmm.
I'll conclude my presentation here. Thanks a lot for inviting me to give this talk. I hope that you have a better understanding. Everyone has a better understanding of what 5G is, what full duplex is. If you have in future, if you have any questions, or if you want to know more about full duplex communications, I have all. So my email ID is there. You can share my email ID with all the participants. So you can communicate to me or over my email ID or on my LinkedIn.
I'll share with the participants. So thank you, Dr. Biswas sir, for his valuable, wonderful talk on full duplex communication for WAN 5G networks. Sir already discussed about the concept of 5G and WAN and full duplex communications with the motivation and challenges. The lecture was really understandable and will be helpful for the beginners who started in full use case examples sir have already discussed. Full duplex and half duplex cellular networks, design. So all the parts are already described. So I think it was a very greatly beneficial to all the parts. So thanks once again for accepting our invitations and for delivering the of our short-term 5G technology. Thank you so much, sir.
Thank you.
Happy Dussehra, sir.
Same to you. Same to you and same to everyone.
Thank you, sir.
Yeah. Have a good evening.
Sir. And yes, sir. Good evening. Happy Dussehra. And I also thankful all the participants who have invested their valuable times in the time in our short-term course. So without your participation, it was not possible to complete. So we are grateful to all of you. And on behalf of Madinapur Institute of Technology and Department of EC, we really thankful to all of you. So happy Dussehra to all of you. Thank you so much. So okay, now participants can leave.
Okay, thank you, sir.